Okay, here's another Heathkit project, and this one is different from all the ones I've done before. First off, it's not test equipment related. And secondly, it's a new build. Unbuilt Heathkit. This was quite pricey, as pretty much any unbuilt Heathkit is these days. I paid over $1,000 for this. I just got the urge and decided to splurge. So I'm going to be doing a complete build video on this, unboxing, build, and circuit theory demonstration, anything that I can do it up complete. So I can't refer to Chuck Penson's book in this case because it's not test equipment, and even though he has a companion book for Heathkit hi-fi and audio equipment, as well as one on ham equipment, the hi-fi and audio one doesn't cover things like mic mixers, so it's not part of that book. The manual says it was produced in 1975, so sometime during the 1975 catalog year is when this product was first introduced. I have not been able to look at a 1974 catalog to see if it might be mentioned in there. And the only 1975 catalog I've been able to lay my hands on is a December 1975, which is what this page is excerpted from. And it's not called a new product at this point, so I don't think it was introduced for the 1975 December issue. But probably the spring catalog would have had it new, possibly the December 1974 catalog. Anyway, let's call it 1975. And they're associating with taping. And they show some people jamming in their house, a bunch of hippie long hairs with their guitar amplifier and lots of guitars and piano and microphones. And I guess that's probably what they kind of aimed it at. Stereo mic mixer. I'm used to seeing mic abbreviated as MIC, but in fact, at least in the 70s, it was a common abbreviation to use MIKE, like somebody's name. So anyway, stereo mic mixer. A hi-fi mixing console, unmatched in versatility and value. High fidelity performance, the wide response, 40 hertz to 20 kilohertz. These days you'd expect it to go down to 20 anyway, but 40 is pretty useful. Plus or minus 1 dB, and low distortion, 0.5% of the new solid state, there it calls it new, TM-1625, will give you clean, like mixing capability, like. I have no idea what they mean by that. Like mixing. Oh, maybe it's new age, huh? Like, cool, man. I don't know what they're talking about. Maybe it's a misprint. I have discovered a number of times in Heathkit catalogs that, you know, somebody probably came up with some good copy, and then whoever transcribed it onto the printing plates, or, you know, the page layout, stage, whatever, saw something and just said, oh, that looks weird, I'll fix that, and it never got caught. Famously, Heathkit produced a piece of test equipment with Kelvin connectors, and the first issue of the catalog called it Kevin connectors, so things like that happen. Versatile switching for complete flexibility. Each of the two outputs has its own master level control and meter, so they can be switched for use in stereo or mono. The 6 inputs include 2 high-level auxiliary inputs for disc or tape sources, and 4 mic inputs, which are switchable in high impedance or balanced and unbalanced low impedance, for use with any type of microphone. Well, not for phantom-powered ones, not directly. The 4th microphone input has a pan control to adjust its apparent location from left to right or anywhere in between. All 6 inputs can be individually switched to left, off, or right channel. Well, That's not true of mic input 4 because it's not switched, it's panned. Access to the mix bus permits paralleling added mixers for extra inputs and outputs. 2 output monitoring systems, a pair of backlighted meters with 2 switch-selected ranges, plus a pair of LEDs with adjustable threshold, show instantaneous peaks faster than any meter. Handsome in black with walnut-stained veneer end panels. Build this quality mixer into your recording system now. Then they give you the specifications. Shipping weight 12 pounds, mailable. From the December 1976 catalog, it has a smaller presence. Like they're already kind of backpedaling it a little bit. It's not a highlighted item. And they condensed the text a little bit. The price is still $129.95, same as the December 1975. So they just start off right away. They don't have all the hippies, young people playing guitars. They just go straight to the specifications. Wide response, low distortion, and they still say lifelike mixing. Here it's fixed. They fixed it. So we got the lifelike mixing. I don't know what that's supposed to mean, even when it's lifelike. I don't know what, is it dead-like mixing? Copy editors, right? Marketing people. Each of the 2 outputs has its own master level control, blah, blah, blah. Pretty much says the same thing with fewer words as the other one. The specifications are pretty much identical. And that's all it says about it. They're not really pushing it very hard, even 1 year after it came out. I wouldn't be surprised if they've already determined that it was a dud product and they're just selling off stock, and you know, it probably disappeared pretty quickly, would be my guess. The next catalog I have after 76, I don't believe it lists it. Alright. The seller had opened this up just to show that everything was included. So I've reopened it. It looks like the box got kind of wettish at some point, but the contents don't look like they got wet. There's no water stains on the manual. And we've got important notice. Make the following changes in the manual. Various, and it looks like replacement part list. And a totally useless parts order envelope with lists of Heathkit locations. They show only one in Illinois. Well, they say Chicago and then Downers Grove. I think the Downers Grove one is definitely not the one I used to go to, and the one I did go to I don't think was technically in Chicago, but it was pretty close to Chicago. The general build guide. Hello! Bob Ellerton, technical consultant. I remember these things. They introduce themselves to you. They'll be their silent partner unless you need them. More stuff. Just general changes in technical consultation. Phone numbers are different, so on. And then we've got the goods. But I won't go further on this until I actually have time to work on this. Alright, let's unpack this guy here. A little bit of bubble wrap. The front panel graphic, which is an adhesive-backed flexible plastic. That might cause me some difficulties if the adhesive is dried out. And then we have the rear panel, mixer bus, output, aux inputs, peak level adjust, 4 mic inputs, line reverse, the front panel, one of the more complex panels with all the angles that I recall Heath making. The plain aluminum bottom panel. The circuit board, it's single-sided, silk screen, and solder mask. Okay, some typical Heathkit padding. I remember this stuff, like quilted toilet paper. Okay, we have some more metal parts. These are the side panels. The ungrounded power cord, bundle of wires, cables of various sorts, power transformer, these look like the wood side panels. Yeah, those rubber bands have perished a long time ago. Oh yeah, nice wooden sides. And that's the bag of electronic parts with most of the parts removed. Well, some of the parts removed. This is transistors and solid state components. And this is most of the other parts. There are the transformers, angle brackets, shields, and then, I'm sorry, that's not the transformers, those are the meters in the styrofoam things. And then the balancing or unbalancing transformers and sliders primarily, and switches. Alright, let's take a look at the manual for the TM-1626. This is an original manual, but when I obtained it, the binding was starting to come apart, so I sheared it off and punched it for a wire binding system. It also helps it lay flat, which is advantageous for the build. I'm doing this part of the video before I actually build the kit. So we've got the usual picture and table of contents. The Heathkit TM-1626 stereo microphone mixer is a 2-channel mixer for use with tape recorders, public address amplifiers, sound reinforcement systems, and audio-visual presentations. It features 4 microphone inputs and 2 high-level, which I think by today's standards is like line level, auxiliary inputs. Each input can be switched to either channel or turned off. Each input also has a separate volume control, and each channel has a master volume control. Rear panel switches allow you to switch the microphone inputs for either low impedance balanced microphones or high impedance unbalanced microphones. The number 4 microphone input has a pan control, so you can pan the signal from one channel to the other. The mixer can be wired with 4 standard phone jacks, which are included with the kit, or 4 so-called Canon jacks, which are not included. these days we call Canon jacks XLR connectors. And practically every microphone uses that style. 2 VU meters on the front panel allow you to monitor the mixer output levels. These meters have 2 ranges selected by a front panel switch to provide output reference levels of plus 4 dB or plus 10 dB. 2 LED peak indicators on the front panel can be set by rear panel controls to indicate any desired output peak level. Other features include a fully regulated power supply, all solid-state circuitry for long life and dependable service, slide controls for easy visual monitoring of the control settings, and a sloped front panel for easy operation. So we've got the parts list, and I'll say at this point, I'll probably reiterate when I start building the kit, but the kit is pretty old, almost 50 years old, and even though none of the components have been powered up, electrolytic capacitors and so on tend to dry out. Certain other types of capacitors tend to drift or go bad. Carbon composite resistors tend to gradually increase in resistance over time. So I actually went through and took note of the tolerance. Some are 5%, most are 10% in the carbon composite resistors. And I found at least 80–85% of the resistors in the kit were in excess of 15%, sometimes more than 20% out of tolerance. So I consider that to be too far, and as a result, even though there were a few that were still in tolerance, I just went out and bought all new carbon composite resistors. They're actually carbon film, not carbon composite, but they're still carbon resistors. I would have liked to use metal film, but in through-hole configurations, half watt, I was finding a lot of availability issues. It's really getting hard, you know, when you have a specific idea these days on what components you want. If you're not using service mount and you're working with vintage stuff, sometimes it can be very difficult to find stock. Certainly I could find stock on some values, but I wanted them all to be, you know, the same series and so on for uniformity of appearance. And so I went with the carbon films, which are better than the original carbon composites anyway. And I used all 5% instead of mostly 10%. Anyway, so all the resistors, there are a few metal films that are included. There are a few so-called precision types that are either 1% or 5%. Most of the capacitors are disc capacitors, ceramic discs, or electrolytics. There are only 2 mylar capacitors, and those are polyester capacitors that tend to be good for a long time, so I replaced the electrolytics as well. Ceramic discs tend to be good practically forever. I have no reason to believe that any of the semiconductors are in need of replacement. And then, of course, the parts breakdown and continuing the inventory, which I have not yet done. Getting into the metal parts, all the brackets, odds and ends, grommets, ferrules, cardboard insulators, switch insulators, wooden side panels, VU meters, feet, fuses, fuse holders, connectors, LEDs, classic Heathkit nut starter, and a wire nut. Then we'll get into the step-by-step with the about 1/4 of the circuit board, then the next quarter of the circuit board, the center of the lower part of the circuit board, the lower right quarter, the upper right quarter. And so far this is all just components like resistors and diodes. Then we go back and start working on the upper left quadrant again with transistors and capacitors. Lower left, additional lower left, lower right, and upper right. Then we start putting on the slide potentiometers. And a bunch of slide switches. Then we start wiring the chassis, connecting up RCA connectors, potentiometers, slide switches, fuse holders. There's a fold out with details on mounting terminal blocks and the transformer and some other things. The usual excellent illustrations, mounting the VU meters and the lamps for the VU meters. More of the same, mounting the LEDs. Mounting the circuit board. Mounting some more case components. Cutting up a ribbon cable to use as a wiring harness, and then fanning out the wiring harness. More on that. Connecting up the wiring harness between things on the front panel that are not on the circuit board and points on the circuit board. Wiring up the power transformer and some of the switches and things. Some more case assembly or chassis assembly. Working with a 3-core shielded cable. I believe one of those is required for each of the microphone inputs. And then there are separate details on whether using the 1/4-inch phone or tip ring sleeve type jack with the adapter brackets, or using the native XLR or Canon connectors, which the chassis is basically set up for. In order to mount the smaller jacks, you need to use the adapter plates. More wiring. More fold-outs for wiring. And as usual, Heathkit likes to fold up some cardboard to make some insulators. This is no exception. And then a diagram or two on wiring up phone plugs and Canon plugs. Initial tests. Operational checks. Description of the front panel controls. It's on a fold out. Operational instructions. All sorts of good ideas. In case of difficulty, troubleshooting chart or charts, specifications, circuit description, and as is usually the case with Heathkit, I think it comes down to the impatience of the engineer, or sometimes you wonder if the person who wrote the description really was associated with the person who did the design, or people who did the design. Some of them are written by people who seem to really know the circuit and want to explain it, and other ones are written for the most rank beginner, and it just sort of says, well, these parts over here do this, without telling you how they do it. And this particular manual is written in that second style. It doesn't really explain circuit theory, it just walks you through the circuit and tells you what each section does without going into much more explanation. And there's a rear panel diagram across 2 pages. Circuit board X-ray views. Circuit board voltage charts. Front and rear. Semiconductor identification chart. And then normally there would be the fold-out schematic there, but when I bound this I cut it off, and we'll look at that next. Alright, I've decided to set up a little space in my basement shop. On the workbench I have a cup of about 50% diluted muriatic acid, some Q-tips, a plastic container of cool clear water, a dry plastic container, some little pieces of used t-shirts, and I'm going to try 2 or 3 different methods of cleaning these. I also have the only fairly plain abrasive cream cleaner that the hardware store had, and it comes from the UK, the pink stuff. There's a lot of other abrasive ones that have preservatives left in them that leave films on the surface after you clean them, and I didn't want that. This stuff does not seem to contain anything that's going to stick around after I use it. So I'm going to try the gentle abrasive approach. I'm going to try with a rag and with a Q-tip. I'm going to try the dunking the leads for a couple seconds in the muriatic acid approach with dilution and rinsing and a place to put the finished components. I also got a new box of black nitrile gloves, slightly textured. I think they're slightly thicker material than the blue ones I usually use. So here's a capacitor with what appears to be simple rust on the leads. I'm going to try the dunking method on this one. Well, quite a bit of it did come off, but some of it's still on there. I'm going to try the abrasive approach. There's a little bit of it on a piece of t-shirt cotton. It's not perfect, but a lot of gunk did come off. I think that's good enough for soldering. There I've got all the capacitor leads cleaned up, reasonably shiny. The abrasive method seems to be working pretty well on components with larger leads like capacitors. I don't know that it would be that easy to do it on components with tiny fine leads like transistors, so I may go back to the acid method for that. I'm also going to try some larger things now, which will be harder to do with the abrasive, and I'm pretty much going to have to rely on some sort of chemical approach. Either that or just scraping with a knife or something. Here's one, for example, that ground lug is pretty corroded. The tabs aren't so bad, except for the one associated with the lug itself. I'm going to try this with the muriatic acid on a Q-tip. Well, that cleaned up in just a split second. If there was ever any plating on that part that was corroded, it came off instantly. Personally, I think there was no plating on that. I think it was a mismanufactured part. But I think I've got it cleaned up at least well enough to solder decently in the places where it needs to. And now for these slide pots, the terminals aren't too bad. I think I'm just going to try the abrasive method on these. Maybe a little bit of the abrasive cream on a Q-tip and then just wipe it off. I don't want to get that near the acid. Well, I tried the Q-tip with the acid and I tried the Q-tip with the abrasive, and neither one of them were doing a very good job. I worried about the acid wicking down inside the pot, so I gave that up very quickly. Ended up just scraping lightly with my X-Acto knife, and that did the quickest and I think best job. for these particular parts. Yeah, scraping with the knife was the way to do this. Fastest, safest for the part, easiest. And now for the circuit board mounted slide switches. 6 with 8 pins and 2 with 6 pins. I think for this one it's going to be too hard to scrape them on the inner surfaces, so I'm going to go back and try the acid approach. The terminals are much bigger and I'm less worried about accidentally wicking some corrosive material down into the guts of the switch. So I'll start out with the Q-tips and the acid. Okay, all of those are done. There didn't really seem to be that much corrosion on those. The plating seemed to be of a different kind. And the larger diodes and LEDs, I used the abrasive cream on the diodes and just scraped with my X-Acto on the LEDs. I saved these small transistors for last. I found that they were best done just with scraping with the X-Acto knife blade. It's too close to the acid, too hard to wipe off, get all sides of the leads cleaned off, and you can't get in between the leads for the abrasive cream method. So delicate scraping, and these weren't too bad. They were pretty clean. These had a lot of corrosion on them, so it took a bit more work. I forgot there was another bag of 2 different kinds of transistors. I had to scrape all of them too. Alright, small task. I have to make another one of these. A fiber washer. There's one missing from the kit. Heathkit just calls it a number 6 fiber washer. It's a 0.375 OD, a number 6 clearance hole for the ID, and 3/32 inch thick. To that end, I bought a 4-foot piece of what I hope is comparable material from McMaster Carr for a few dollars. Okay, there it is. All 4 feet of it. That's the minimum length I could buy. Luckily it's not expensive. And it should be a pretty simple thing to make some of this. Looks like a number 25 drill is the perfect fit for the existing washer. And it'll be easier to drill the hole in this rod stock than it will be to cut it first. So I'll start with cutting a short piece that I can chuck up in the lathe. Go in there a little bit more, just use up the material. And now I'm going to face the front of it because I didn't cut it completely square. Alright, they're different color, but they're the same thickness, same diameter, and they have the same hole size through them. Should work fine. And I just made a few more, but I could make a bunch more of the same size out of this drilled piece yet. Alright, well, the first task is always to inventory the parts. And I know I have all the resistors because I bought a completely new set of resistors from DigiKey in all the bags, because the old carbon composite ones had aged so badly that they were just way out of tolerance. The circuit might have actually worked okay with the old ones, but I figured, you know, how often do you get to do a new Heathkit build these days? I want it to work as well as the Heathkit design would allow. And I also bought all new aluminum electrolytic capacitors. So I'm going to just not even bother checking the resistors because I know I have those. At least the carbon composite ones. I need to look at the metal film ones. So here's the first parts bag contents. Some of the contents were in smaller bags. And of course these things aren't in any particular order as I recall, and it's just, I don't know how they figured out what was going to go into each bag. But I need to find them on the inventory and mark them down. And here's another bag of parts all spread out. So far I've found a number 6 solder lug. There is supposed to be one, but they did an errata to increase it to 3, and I found a parts bag with 2, so I'm presuming I'll find the original one to add to that somewhere in this bunch. And then I found one of the transistors. I was one short, but it's possible, I know from past experience, that sometimes you'll find what appears to be a missing part in another parts bag, so I'm not despairing quite yet. Alright, I've sorted the parts into individual plastic bags according to general type or part of the assembly. I've got 632 hardware in there, and 442 and some really large pieces in that bag. General hardware, capacitors, specialty resistors, transistors, diodes, all in separate bags so I can find them quicker. And the only thing I found that was actually missing, the one transistor that appeared to be missing, was found just rattling around loose in the bag down here. I think I caused that because I'd opened the bags up earlier just to generally see what was in them, and I think that one probably fell out and got just stuck in the bottom. So luckily I found that I don't have to go out looking for a replacement obscure transistor. Alright, I'm getting ready to start the assembly. And on my bench here at the moment I have a new acquisition. Just came in. I did a preliminary test, but it's a IB1101, IB1101. It's one of the Nixie tube frequency counters. It does seem to be partially functional. It has enough wherewithal to display zeros, which isn't any trick. That just requires power, but it does require that at least some of the driver chips are working, and it does power up with a default value in the counters, which then gets cleared at the next gate. So that much is working, but it's unresponsive to input. So that's a project for another day. Alright, there's the circuit board. It's actually a nice fiberglass circuit board, single-sided, silk screened on the front, and with a blue solder mask on the rear. Fairly good sized circuit board. I don't see any hint of corrosion. It was inside of a sort of a saran wrap type of plastic sealed envelope, so not exposed to outside contaminants. Looking at the first page of assembly instructions, I've pulled the resistors out from the various bags, so I have those at the ready, and I have to make 4 jumper wires. 3 of them are 1.5 inches long and one of them is 1.25 inches long, to be made from some of the red wire that was included with the kit. And now I've got those. Following their instructions about how long to cut the wire and how much insulation to cut off, the insulation ends up being a little bit short, but that's fine. It's not going to contact anything else. I'm using my good old RG Company model Mark II half-watt wire lead bender, which I used early in my career when I was a assembly technician before I got my degree and became an engineer. Yeah, when the company folded, I just had this in my toolbox and I took it, but it used to belong to them. I'd actually sanded it down a little bit because to fit the typical spacing for a half-watt resistor, it was just a little bit wide. This got a lot of use, but it's still a very handy tool. So I place the resistor in the slot, hold it down with my thumb, see if I can get that in the camera, and then just push the leads down to the sides and lift it out. And we've got the bend. Precise and consistent. And now all of the leads for this page of the assembly have been pre-bent. Well, the components for half of the page are soldered to the board. I'm not real fond of the way that the solder is flowing on the pads. Part of the problem is that Heath used this rather poor circuit board design philosophy in those days, where they had really large lakes of foil that would just heat sink the heat away, and it's hard to get the pad up to temperature. But I've got a reasonably powerful soldering iron, and I'm wondering if the problem isn't primarily that there might in fact be a little surface oxide on these pads. And I'm thinking if I should try to clean them up a little bit before I go further. I used my Dremel Micro, or whatever they call this, the 2050 or something, with a little wire brush and just gently touch the pads, looking at it with my magnifier, and it did look like it shined them up pretty well, so maybe that'll make a difference. Well, I'm not at all happy about the quality of solder joints I'm getting on here. They're doing the job, they're making good electrical contact, and they seem to have at least some mechanical grip, but it's like the, I almost wonder if something on the silk screen is degenerated with age, so when it gets warm it outgasses something that's making it hard for the solder to adhere to the pads. Because initially I'll get them warm enough where the solder will just flow pretty as you please all over the pad, nice wetting and everything, and then just like boom, all of a sudden it doesn't want to stick to it anymore. I'm guessing that's something to do with the age of the circuit board. I've been taking very careful resistance measurements from the leads to the pads and to adjacent pads that are connected to the pads that have just been soldered, and I'm getting excellent conductivity. So I think it'll be alright, but I wish I was getting better quality pads. And just to see if I had an issue with heat, I even fired up my old Weller soldering iron, which made no difference. And another couple of jumpers and more resistors for the next page of assembly. Here we're going to be working, whereas here we worked on sort of the upper left-hand corner of the board with just resistors and jumpers. Now we're going to be working down in this area here. All leads bent. For this next pass, I tried a good old pink pearl eraser, which I used to use to clean edge card connectors, or card edge connectors, depending who you ask, with good success. And then I went over it several times with Tech swabs and isopropyl alcohol. This is from the last pass. The first few passes, they were coming out just black. So there was definitely some gunk coming off, and I don't think it was all just eraser residue. I think there was some oxide buildup on there. We'll see how it solders in this section of the board. I noticed a little glitch, and my camera won't want to focus on it. And again, we're looking at these globby soldering joints because I've noticed what's actually happening here. Well, I still am not sure the cause, but initially the solder will wet the pad very nicely, so I know the pad's warm enough to keep the solder melted, but then it wicks up the lead and wicks off of the circuit board. It's like it really wants to be wetting the lead and not the circuit board. It's if it has no place else to go, it'll stay on the pad and look like it's a nice wet joint instead of a cold joint, and then it'll suddenly go whoosh up the lead and leave the pad almost dry. And usually I kind of like scrape the iron around back and forth, and all of a sudden it'll go back down and wet the pad a little bit. But in the course of doing that, I've added a little bit too much solder, and it's not flowing. It looks like they're not cold joints, but they're very globby joints that don't flow nicely around the pad. Yes, they're adhering to the pad. Yes, they're adhering to the lead, and by they I mean the solder. And it's making a good electrical connection and at least an adequate mechanical connection, but it's just shit. I think that's got to be something about the plating they're using on here, where the metallurgy or whatever, it does not want to wet this if it's got somewhere else to go. Maybe somebody who knows more about this can weigh in. Anyway, there's this pad here, and it kind of flows around here, but right here there's a round thing, and this is supposed to be a pad right here that only goes to those two pads, or those two leads. It's not supposed to connect over to here, but there's this round area. It's almost as if a round pad got dropped on the artwork and shorted those out. And I checked the X-ray view in the manual, and here's the same two things. So it's actually like a round aberration right in here connecting these across. So I'm going to have to get my X-Acto knife out and cut that. I wonder if every circuit board they made in this batch had the same defect. Maybe in every batch. Okay, the first two pages of assembly, which is just resistors and jumpers so far, that's completed. I would say we have the bulk of the resistors on the board now, but there's still quite a few over in this quadrant. I've determined that there's another problem here. It's not the only problem, I'm sure, but thinking back on other soldering jobs I've done that were problematic, which is very few, but there are some, if the holes surrounding a component lead, you got the pad, then you got the hole, if the lead is considerably smaller than the hole, then the solder has problems bridging the gap. And then you run into surface tension issues. You apply more solder to try to get it to just glob up and bridge the gap, and then you've got more solder quantity there than surface tension can cause to lay nicely, make a nice fillet, and it just naturally wants to pull it into a blob then instead of a nice I'll illustrate it. You've got the hole in the circuit board, and if you've got a fairly close tolerance with the lead, the surface tension will make the solder make a nice curved fillet like that. But if you've got an oversized hole, the surface tension won't make that fillet. It'll try to stick to one thing or the other, but not both. It'll want to glob up around here, and maybe a little bit on the sides, but it won't want to flow across. And so you add more solder, and pretty soon you've got a ball of solder like this that would rather stick to the lead than bridge the gap to make a fillet out here. It's too much solder by that point required to fill the gap. And I have had issues like that in the past when I've had some really poorly made kits, like some of the ones by Ico or something. It's like the smallest drill bit they have is 1/8 of an inch. And you've got these little component leads that are supposed to be soldered to those. Those things have been terrible. You pretty much have to fold the lead over the pad and then just solder it instead of trying to get the solder to make a fillet properly. And that might actually be a way to make these work out better on here. The pads are pretty big. I may consider doing that, but I'm not too concerned with beauty on the solder joints as long as they're functional. And by not folding them over like that, at least it allows for the option of removing a component later if you need to replace it without quite so much of a mess. Alright, some diodes have been added. A couple of 1N4148s here and here. Those are like 1N914s. And then about 8 germanium diodes scattered around. Yeah, 4 over here and 4 over here. And here's the parts for the next stage. Bunch of resistors, a jumper, a couple different kinds of diodes, and another precision resistor, which is probably wire wound. Alright, now all the resistors and 2 Zener diodes and 1 jumper have been put in this section of the circuit board. And I think this is the final set of resistors and diodes and a jumper that go on the circuit board. Alright, all of those components are on there now. All of these guys through about here. Okay, now we're getting out of the resistors. We have 10 microfarad electrolytic capacitors for this first step. These are ones I bought new to replace the iffy ones that came with the kit. 4 disc capacitors, these are originals. And then 3 different kinds of transistors. I've gone through and cleaned up the leads. They were buffed before and now they're wiped with isopropyl, and these shouldn't need it because they're brand new, but based on whatever other experiences I've had so far, is the solder is sticking to the leads well enough, it doesn't want to stick to the circuit board pads. So I don't think this will be the issue. My concern is that the soldering iron might need to stay on the pad so long to get the solder to stick decently that it might damage the transistors from excessive heat. I'm not really sure what I can do about that. So now for the 4 channels, the 4 primary channels, that's the mic inputs. We've put on the transistors for the preamp and 2 capacitors, an electrolytic and a disc capacitor. Duplicated that to a total of 4 places. And then there's a couple of amplifier stages here, each with a transistor and 2 electrolytics. These new Nichicon electrolytics are greater in diameter and slightly greater in lead spacing than the originals provided by Heathkit, but they're shorter, so I could allow the capacitors to sit up a little bit on the board to allow the leads to splay inwards a little bit to fit the circuit board holes and still have the top slightly lower than the originals would have been. Okay, a bunch more transistors, 4 different types. And these are going to go on the lower left quadrant of the board, down in this area. Alright, all those transistors are in there now. Some more 10 microfarad electrolytics, 4 of 100 microfarads, a couple of 0.05 microfarad disc capacitors, and a couple of 680 picofarad disc capacitors. And these are going to go in on the lower left quadrant, really the densest part of the board as far as components go. And I get a little worried in this area because everything is so close and many of the holes are right next to each other instead of being connected by a length of circuit board foil. And with the tendency of the solder to wick away from the circuit board pads, once you heat up a lead in one hole enough for the solder to flow, it wants to wick away from adjacent leads that you've already soldered, and it can get into be a real mess. So I have to be very careful with this stage. Alright, all those parts are on now. Alright, now some components for the lower right quadrant of the board. A few more 10 microfarads, a couple of 0.22 microfarad mylars, the remaining transistors, 4 different kinds, another electrolytic capacitor for the power supply. And alright, those components are on now. Starting to look like an assembled circuit board, except for all those bare areas. And now the 4 unbalancing transformers for the microphone inputs, another large electrolytic, and the 4, I presume these are mu metal, shields for the transformers. And the 4 transformers are on the board, and that other electrolytic is here. I need to put on the shields for the transformers now. Okay, those cans are on. They fit extremely tightly around the transformers. They just barely go over them. And then there's really close tolerances with the jumper wire, which is not the same point in the circuit. So I had to use a small screwdriver to bend the leads right where they come out of the holes as far away from the transformer shield as I could get them to go. That's a little close, Heathkit. Okay, now we have all the slider potentiometers. There are 1, 2, 3, 4, 8 of them that are 50 k ohms, and one of them that's a 10k. And now all the potentiometers are on the board. I should note that I use DeOxit Fader F5 on the pots before I assemble them to the board. They're not dirty, they've been sealed up since they were made, but in case there was any oxidation or just whatever settling on them from the packing material, for example, I wanted to clean them up a little bit, lube them up, and then I used good old regular DeOxit D5 on these switch contacts here. There are 6 3-position switches with 8 lugs and 2 2-position switches with 6 lugs each. So I've got them hit with that and exercised back and forth a bunch of times, and then they'll be assembled to the board. Okay, and all those switches are soldered on. And this, by the way, is the completion of the circuit board assembly. The only thing that still goes on there are some wires that terminate in various places. 4 places for each transformer. There are wires, I believe those are from the microphone jacks. And there are a few places scattered around where a wire here or there comes and goes. A few wires there, which I suspect are going to be associated with the power transformer. Yeah. Alright, we move to the chassis assembly and start with the rear panel. Nicely wrinkle finish painted with a good quality silk screen on it. And the first instruction is to remove the paint from around those 4 holes and this one, which I suppose will have a ground lug because the power cord entry is right there, and then another one down there for whatever gets mounted to that point. I'm going to mount these 2 phono jacks to the rear panel in these positions with some 440 screws, lock washers, and nuts. And the diagram shows us the orientation. And there are those. And now I'm going to mount 4 more phono jacks at these other 4 locations. But unlike the first 2, which are mounted to paint scraped areas for good electrical contact for grounding, these are electrically isolated from the chassis, or they will be, and that's accomplished by using these fiber washers between the metal part of the jack and the chassis, and also not scraping the paint off in those locations, and by the screws themselves being nylon screws. So we get electrical isolation that way. And that's for avoiding ground loops, so you don't get multiple pieces of grounded equipment all trying to be the ground and causing current to flow through the ground, which can cause hum and other issues. It's good practice. Okay, those are mounted. Using the insulating screws and washers or bushings. So now for the two rear potentiometers, which are used for, what are they used for? I think they're set for setting the sensitivity of the peak detector for the left and right channels. And they have a recessed screwdriver type shaft so they're not inadvertently bumped. To get them to come out more or less flush with the outside of the panel, there's a nut put on at a specified distance, and then there will be another washer and a nut on the outside. Okay, those are on. Next, I'm mounting 4 of these screwdriver slot adjust slide switches using some number 6 black anodized screws. Okay, those switches are mounted. There's no need for lock washers or nuts on these because the screws thread right into tapped holes in the flanges of the switches. And now for the fuse holder, 1 6/32 screw, a nut, and 2 lock washers. Okay, that's on. Can't tell what's there from the other side. And now a 4-lug terminal strip, again with a 6/32 screw, 2 lock washers, and a nut. And this will go at this location with the paint scraped away, so it gets a good electrical connection to the chassis. Then I mounted this slide switch, which is the line reverse slide switch. That's again useful for correcting hum issues. And next up is the power transformer. The instructions told me to cut the leads to specific lengths and restrip them. Those are the primary, and then the secondary leads are, at least for the moment, to be uncut. For mounting the transformer, the instructions strangely don't instruct me to remove paint from the transformer mounting tab that will be associated with this hole that they told me to scrape the paint off for electrical connection. So I think that's an oversight in the instructions. It doesn't do any good to scrape the paint here and then have a nice thick layer of paint on this that's supposed to be making connections, so I'm going to scrape that off. Alright, the transformer's right behind there. And there it is, with the secondary leads to the right, as it says to do in the instructions. Alright, here's the so-called top panel, chassis top panel. I've removed some paint from the inside of that screw hole. And I have 2 lamp holders, 2 flathead screws, lock washers, nuts, and a ground or solder lug. And that will be assembled like this. Well, a problem has surfaced with these countersunk bolts. When the head is flushed, there's still a bit of the countersinking taper sticking up above the inside surface of the plate, and that means that the flange on the lamp socket doesn't sit down flat, and so the nut, even when tightened, doesn't really secure it, and it can sort of swivel around on that point. And there's also supposed to be some friction between this large flange plate and the inside surface here to assist in keeping it from sliding around. So I need to come up with something to offset this lamp socket flange and have a clearance to accommodate that little bit of the head that sticks through. So I think it's down to the shop. Okay, I've made a couple little pieces of 16th inch aluminum, or yeah, 16th inch aluminum. I've cut it out on my metal shear to 7/8 by 7/16, which is the size of the flange on the lamp sockets. I've marked and dimpled the location of the hole, and I've got a drill that's oversized to the point where it should allow for that taper on the head of the screw. Alright, so I have those two made now. Crude but hopefully effective. Well, one of the two number 53 lamps has a defective nub on it. It doesn't come up nearly as high as it should. It's supposed to be peaked and it's just flat. So trying to salvage it, I made a little ring out of some I think number 22 gauge bus bar wire that I'm going to try to solder on top of that, and maybe that will have it make better connection. Well, it seems to be a bigger problem. I've got my power supply hooked up with 12 volts, and this bulb in here, if I push it into the socket, it lights up, but it isn't making it on its own. It's and that was the good bulb. Here's the bad bulb. It also, I can't even push it in there. If I get it just right, I can get it to light up. Huh. Wonder what's gone wrong with these things. If these, something has gone wrong with the sockets over the years. I don't know. Yeah. These things are dead on arrival as far as being functional. What can I do about that? Well, the only solution I can come up with is to buy some comparable bayonet sockets. I already bought some new lamps on Amazon, and I found this VCC, which is Visual Communications Corporation or Company, Lee Craft Miniature Bayonet 7 Series sockets. And if I scroll down through all of these, I find the model 720, which has exactly the same dimensions as the ones provided by Heathkit all these decades ago. So, let's see, ungrounded terminal. What's that mean? Oh, that just means that normally these sockets are provided with two solder terminals, one for the outer ring of the socket and one for the tip inside, and then the bracket here is not electrically connected to either one, but you can get a version where the bracket is the outer shell and then there's only one solder terminal for the tip of the lamp. So that's a special version, but the version that I want is this kind right here. So that's a 720. And DigiKey sells them and has them in stock. They're not giving them away. About $6.25 eaches. Well, I've ordered a couple of these from DigiKey and should have them in a couple of days. So moving on, the next thing to do is to mount the meters. 2 meters in their boxes with the mounting bracket, the meter bracket, and a 632 nut. One of these meters came with the cover loose inside the box. And I thought, what's going on there? Turns out there's these 2 tiny little screws that fell down into my trash can when I was opening the box. They were just laying loose inside of there. I had to go through all of that with a fine-tooth comb to find both of them. As the instructions note, these meters come with a shorting jumper on them which needs to be removed. Alright, I've measured the coils on these meters and they're just a little bit on the shy side of 1000 ohms, and that means that I can hook them up and do a calculation, and as it turns out, yes, if I apply 1 volt from my power supply, run it through my milliampere meter, run it through a 4K resistor in my resistor decade box, and connect it to the meter, I should get a full scale reading. It should be about 200 microamps. And it is. Can I make it go any higher? Yep. I wasn't hitting a stop or anything. It's a 200 microamp meter movement. And it does seem that yep, the meter's not stuck. Sometimes you get these old meters and they end up being stuck somewhere, but this one seems to be moving freely. And the other meter's reading similarly. Let's do a check on that one. Yeah, it's working fine. And there those meters are mounted on their bracket. The instructions don't tell you or give you any idea how much you can tighten these down. And of course it'd be difficult to calibrate that, but there's no caution against over-tightening, which kind of surprises me. But the meters look okay from the front. Well, one of these leads snapped off the LED, and these were highly corroded. I had to polish them quite a bit, and that might have contributed to that lead snapping off. I'm going to do a test on this and see approximately how bright it is for a given current, and then I'll compare it to some new LEDs I have in my parts bin. I might want to substitute these crappy looking old ones. Yeah, it's not going to look proper on the camera because it doesn't respond to the wavelength of these LEDs very well. But the LEDs, you can see it there, it has kind of a dark spot. It's not diffusing regularly through the front. This is one of the original LEDs. You can even see it there, it's kind of misshapen. 10 milliamps ought to be just fine for a legacy LED. And my power supply is putting out 12 milliamps right now. Okay, I've changed the resistance in my series resistor decade box here to get 10 milliamps, and while the light is adequate, I mean you could see it just fine, but let's compare that to a new LED. There is a new LED with the same current going through it. It's much nicer, much better pattern, much brighter. I'm going to use these. Alright, LEDs and their grommets, their plastic grommets. And the retainer rings. Alright, the LEDs are mounted now. Alright, the remaining switch needs to be mounted. This time it needs a couple of metal spacers, and it uses the same flathead countersunk type screws since it's going through the front panel. Alright, there's the switch, and on the inside. I'm going to mount these 3 spacers with the flathead screws and the 3 fiber washers, the 2 that came with the kit and the one that I made myself as already shown in this video. Okay, the spacers are on. I had to countersink the fiber washers a little bit on the one side to accommodate the tapered portion of the screws sticking, screw head sticking through a little bit too much, just like I did in a couple other places. I think in general Heathkit probably should have used a slightly thicker metal for this panel if they were going to have countersunk screw heads in it, or just countersunk them a little less. Would have worked out better. And now I have the side panels on. They're held on with countersunk screws in 6 places each. Okay, the next step is to put on the decorative panel here, the whatever they call it. Anyway, it's the one with all the fine markings on it, and it's supposed to be self-adhesive. My question is that self-adhesive just totally dried out by now? Duralith. Well, it's still sticky, hopefully enough to stay down with all that surface area. Alright, that's stuck down. It's able to be lifted up if you can grab it from the edge. It's probably not down as tight as it should be. What I'm thinking of doing is sneaking a little super glue in along the edges just to make sure those don't lift up. And then I believe that the aluminum front piece on this kind of goes on like that, I believe, and protects it. I'm not sure that's the way it goes on, but it looks like it might. Kind of like that, which would be a big help. It does seem to be the angle. I'm going to now put on the front and top rails, and they have these channel grooves in them. And for that purpose there are some T-nuts provided that will go with some 632 lock washers and nuts. Alright, those nuts are on through the yeah, and the front plate hangs below as it should, because there's going to be more stuff on the bottom that'll make that line up. And the way it looks from the side is like this. So yes, that front edge of the decorative panel here is held down and protected by this piece. Actually, I could, yeah, that's close enough. There's how the top one will lay on, but I can't do that quite yet because I need access to these 2 screws here when I change out the lamp brackets. But I think there's no reason why I can't add this piece later. The screws will be perfectly accessible even if I put this on at a later date. So now skipping over the top rail, as I already mentioned, the wiring begins. Chassis wiring. And this is the orientation of the chassis they recommend as a starting point. The board is held in place temporarily with 2 sheet metal screws into those brackets there. Alright, FedEx did its bit. I paid the extra few bucks to get overnight delivery, and let's see what I got. Alright, T3 1/4, I guess. Bulb socket bayonet made by whatever brand this is. Visual Communications Company. Well, these are actually slightly taller, but I don't think that'll make any difference. Yeah, that works out great. It's got good springiness on the contacts now that the old ones did not have. This is the other bulb in the other socket, and it's a little iffy. This is the one with the very shallow point on it. It's a little iffy, but it's also dimmer. I'm glad I ordered new bulbs, but I think the sockets are fine. Okay, the new lamp holders are in place, and when I get the new bulbs in, I'll put those in instead of these grody looking ones. The first of the chassis wiring is put in. There's a short jumper from one end of this lamp to chassis ground, and then a wire going to this lamp holder, and then through there to a terminal on the circuit board. So obviously there's a source of power, goes through both bulbs in series, and then returns to circuit ground through the chassis. Okay, now I can put on the top trim strip with the T-nuts in there, going through these 2 holes and these 2 holes. Okay, the screws are on there, and that piece is looking good on there, along with the one in the front. And I've cut a length of multicolored ribbon cable, and the plan has been to lay it on this full-scale drawing fold out and peel back the different lengths and cut each branch to length. Okay, that ribbon cable has been connected out to various pads on the circuit board here. A couple leads of it going to that LED. Other leads going to the 2 meters and to another hole on the circuit board. So basically that hole is going down to one side of the LED, and the other one's going to a point over here, and then otherwise the 4 meters are coming through that way. Alright, I've prepared 2 short lengths of shielded cable. On one end of the cables, the shield wires remove the drain wire, and those are soldered onto 2 pads on the circuit board. The other ends of the cables still have their drain wires. And up next is the all-important affixing of the Heathkit blue and white label, as they always call it. Usually that goes on the outside, but in this instance they've decided that it should go on the inside, and it should go here, like that. So another multi-conductor cable has been cut and soldered to several points on the circuit board, 6 points. And so far only 2 of the wires are being used. They're going to the other LED. The others will be connected later, along with the shielded cables that were done in the previous step. So now the attention goes to the rear panel. And the first step is to put on this switch insulator on this switch. So next I prepared 5 short lengths of the black wire, which is probably 18 gauge wire, I'm guessing. There's like a 1 inch, a 1.5, a couple of 2 inches, and a 4-inch piece. And those will be involved with wiring in this area around the power transformer. So I've got those wires soldered up to the phase reversal switch. I think that's what that is. Double check. Yeah, line reversal swaps the hot and neutral. Some of them are soldered already, some of them are just wrapped around the lugs, depending if another wire still needs to be added. One of the wires goes down to the fuse holder down there. And now I've got to prepare these two, well, I have prepared these two disc capacitors, 0.01 microfarad, 1400 volt. The lead lengths are different depending on where they're going, and there's 2 lengths of sleeving for the cap that has the longer leads. Okay, those capacitors are soldered on, except, let's see, this point's soldered, but this one here is not, because apparently another wire is going on there. Next we deal with the line cord. I don't think I ever noticed this before on other kits, but apparently Heath had their own power cords made, at least for a while. And the power cord, the smooth lead is connected up to this side of the fuse holder, and the other one goes to that point that has a switch wire and a capacitor on it, and that is soldered. I've cut 2 21-inch long lengths of the black wire, got one end of each in the bench vise, and I'm going to twist them together to make a twisted pair cable. Kind of like that. One of those gets soldered to this switch terminal, which already had a wire on it, and then the other one goes to this terminal strip position, but that's not soldered because there's no other wire yet and it needs to go somewhere. Okay, the primary side transformer wires, all 4 of them, are now wired up to the terminal strip in the positions appropriate for 115 volt AC power. And now the 8th amp fuse is snapped into the fuse holder. Next I have to put in the strain relief on the line cord where it comes through the back panel or the rear panel. Now I've got this rubber grommet to install in this hole in the transformer shield. There we go. The next step involves putting in an insulator made out of this adhesive backed cardboard, of which I'm supposed to cut a piece out but the adhesive has completely gone dry on it. I don't think that, I don't know, I don't really trust that to put another layer of adhesive on, because unlike the front panel, which still had an active adhesive on it, this is totally toast. And yeah, I don't like this. It's really thin cardboard, and I have better options. So I've got a piece of my stock of Mylar, cut to the requisite 1 7/8 by 5/8. And it's folded per the instructions 3/8 inch from one end. And since this is textured on one side, I'm using the outside surface or the matte surface as the outside. That's for better adhesion from the adhesive I'm going to use. I've put some of my Scotch, don't drop it, Paul, permanent adhesive on there, and it goes right down into here. Okay, that insulator's in there now. So now I have to do this little bit fiddly process of putting this plate and this transformer shield and a braided jumper and a label regarding the fuse over the transformer and high voltage areas, held in with little number 6 sheet metal screws, and feeding out the transformer secondary leads and that twisted pair cable I made earlier. Okay. This is definitely a two-hand job. Okay, the transformer shield is mounted with 6 sheet metal screws so far. 2 along there, 2 on the inside of that flange, and 2 more on the inside of that flange. And you can see it's kind of tight in there, and that's why they wanted that insulator, because of the proximity of the fuse in that area. I actually bent the tab of the fuse holder up a little bit to make it a bit further from the sheet metal, regardless of the insulator. This is the transformer shield plate, and it goes on like that. And I've also put a piece of Mylar in this area, once again to prevent any close proximity of the fuse holder from touching the plate, using the same Mylar I used before. And this will get put on with the 3 sheet metal screws, but there's a step in between this and putting it on. This piece of braid was included with the kit, but it was as part of an errata or addendum bag and part of the errata instruction sheets, so it was apparently omitted from the original kit packaging or packing. And I'm supposed to be able to open this up. It's supposed to be like a flattened round braid, so I'm supposed to poke away at it with a tip of an X-Acto knife or something and see if I can open it up into a more tubular shape again on the ends. And that is with the idea of putting the small end of these 2 solder lugs inside that for soldering. Well, doggies, you can actually see that that is opened up. I have used this braid for years and never realized it was made by crushing flat a circular braid. So it's like they use the same machine that would weave a braid around a shielded cable, and then they just flatten it. Apparently that's the manufacturing process. Okay, the solder tabs have been pushed in, and I've soldered the braid to the tabs front and rear. That's pretty slick. I have to remember that trick in the future. And there the shield plate is put on with the braided ground strap. And now the fuse label, per the instructions I've written, 3AG and 1/8 amp in the spaces provided. However, the adhesive is totally dried out on this. I could put more adhesive on the back of it, but I have a better idea. I just made an equivalent label using my Brother P-Touch TZ tape label maker. Yeah, there we go. I noted after the fact that Heathkit recommended putting the label on upside down, probably for better viewing from whatever angle you're going to access this. So I just printed another label and stuck it on upside down. 2 wires have been soldered between the outer terminals of these 2 pots on the rear panel. Soldered here, left open here for future wires. And I've cut 4 lengths, 9 inches long each, of 3-wire shielded cable. This will be for the microphone wiring. There are a couple of ways that I know about to get the internal leads of a multi-conductor cable out of the shield, if it's a woven shield or a braided shield like this. One way is to painstakingly unweave it, starting at the end and working way down till it's all just a bunch of unwoven wires, and then you twist all those up into a single conductor. Another way is to, right where the insulation ends, and then just push the strands away right at the top of the bend so that the inner conductors are exposed, and then use like a little jeweler's screwdriver, which is what I usually would use to unbraid these anyway, and reach underneath one of those and tug it up out of the end section, working it out like that. The first one always comes out hardest, and the other ones come out quite easily. And then finally they're all pulled out, and you're left with kind of a snake skin that's been shed. And then just pulling it between thumb and forefinger, the braid collapses and it gets a little bit longer. And then twisting it between thumb and forefinger, you end up with essentially what you would have had if you'd unbraided the whole thing and then twisted it up, except it takes a lot less time and less eye strain. Okay, all 4 of the multi-conductor shielded cables have been prepared. Insulation stripped, strands twisted, soldered to prevent them unraveling. And the instructions say to set these aside for later. Okay, it's time to install the so-called Cannon jacks, which are female XLRs by Switchcraft. These are essentially the same product that Heathkit had in mind back when this kit was designed. I don't know if they're called Canon connectors because maybe Canon originally came up with the design, but as far as I know, Switchcraft is pretty much the king and has been for a long time in this kind of products. I think they're better quality than any of the other brands I've seen. And in the theaters where I do part-time work, the guys there who were doing the PA and so on say You know, if it ain't switchcraft, it doesn't come in this building. Anyway, so I got those, and I've got the Heathkit hardware, which was provided, which works with either the phone jack adapter plates or the Canon connectors. Okay, the holes were just a little bit tight because there was paint on them, and that would be necessary if you're going to have the 1/4-inch phone jack adapter plate in there. You wouldn't want this bare metal exposed, so it was painted, but that makes it just a little bit tight because these fit in pretty snugly. So I just went around real quick a few times with a Dremel tool and a sanding drum on it and just took it down a hair, removed the paint essentially. Alright, all those jacks are screwed in now. Four wires have been soldered between terminal 2 of the XLR jack and the middle of the switches. Okay, the multi-conductor shielded cables have been soldered up. The black lead goes to pin 3 on the jack, the white lead to the switch, the red lead to the switch, and the shield is so far unconnected. Now the instructions say to wire it down through the ground lug on the jack and then to terminal 1, and that's just going to be a cluster. It's possible to do it, but it's going to be messy, so I'm going to deviate slightly from the instructions and put a drain wire on that. Okay, I've cut the shield a bit short, but not too close. I don't want to overheat these wire insulations. And then I've sweated on a length of smaller gauge, I think it's number 22 stranded wire. And I can slip on a piece of heat shrink that will go all the way down to there and still overlap the insulation on the smaller wire by a little bit. About like that. Alright, I put those heat shrinks on now. And now I'm going to slip some larger diameter over the entire outer jacket and try to slightly overlap that joint. It's going to be difficult the way the wires are splaying out, but I'm going to try to see if I can cover it up just a little bit where there's exposed braid right there. Alright. Now I just have to strip these smaller wires and pass them through the 2 lugs on the jacks that Heathkit stipulates. Okay, those jacks are all wired up now. Okay, there's one more prepared ribbon cable section, and that'll be going on around over in this area. Alright, it's finally time to mate the main mixer assembly with the back panel or rear panel assembly. There's a couple of pages worth of steps hooking everything up. First step is to put a switch insulator on this switch, which I believe is the power switch. And I'm going to have to get the twisted pair of wires from the transformer shield area over to that. I went one step further and put some shrink tubing over those, although Heathkit didn't recommend doing that or mention doing it. Heathkit then wants me to use some more of that adhesive back cardboard to make a little cover to go over the switch. And I've achieved essentially the same thing by putting the shrink wrap. There are no exposed connectors there, except for, of course, the other one here, and I can solve that by putting another piece of shrink tube over it, which I'm going to do. Yep, right down there. So there's no electrically accessible points on that anymore, so I don't need to build that kind of kludgy insulator that they recommend. The next step is to land all these 3 conductor shielded cables from the microphone jacks to these locations on the circuit board. And once again, they didn't really make provision for how large the bundle of wires is for the shield, so I'm going to do what I did at the other end. Cut them a little bit short, sweat on a length of more reasonable cable, and then put some shrink tube over it, and then land the smaller cable in the circuit board hole. Okay, I've double insulated those, so I've insulated the shield and then put another shrink tube over the end of the cable jacket, so there's no exposed shield connection there. The only connection is right there at the tip. And I've done that 4 times for the different wires or cables. Actually, before landing the shielded cables, the 3 wires from the secondary of the transformer go to the circuit board, and they just barely reach. And then this ribbon cable that comes down here and services one of the LEDs, the other 4 conductors end up on the wipers and the outer 2 of these 2 pots. The elements are in parallel, so it only takes 2 wires, and then the wipers take the other 2 wires. And now we have these 2 single conductor shielded cables coming down and landing at these 2 jacks. The shields are not terminated up at this end, and they are at this end. That's good practice. Single end terminations. And these are the jacks whose ground sides are connected to the chassis and paint was scraped off. So that is the single point ground, whereas everything else is insulated from the chassis here, and the shield is just landed back at the circuit board, but not at this end. I'm sorry. It is landed at this end, I'm sorry. Yeah. So these are the jacks that are lifted off of the circuit board with the insulators, and the shield and center conductor are landed at the jack. They're not making a ground connection here though. And then the other end also has the shield and center conductor, which will be landed to the circuit board. Alright, all of those are soldered on. So these jacks shielded cables are now connected up to here. And I put a little bit of shrink tubing on the shield, or the drain wire from the shield, just in case it gets folded over weird and shorts out to something else, it won't short. And now the ribbon cable from these 2 jacks comes up and connects to these points. And now the 2 screws that were temporarily holding the circuit board in place have been taken out, so the board can be flipped down, and then all the wires that were stuck through from the rear either need to be straightened up so they're not likely to touch something else, or actually clipped off more or less flush with the board. It would have been nice if they provided a document showing where all those are from this side, because otherwise you got to look at the board and flip it over and try to find the same place. And it'd be nice to assume that all the wires come straight through and couldn't possibly touch something else, but I found at least 6 that were right on the edge of either touching another through-hole wire right next to it or touching the lead of a component that should not be electrically connected. So I've looked through as carefully as I can on this, and hopefully I got everything. Alright, the board is put back in, and that was a bit of a tricky proposition actually, trying to juggle it without pulling these wires too tight and get all the pots and switches to line up with the slots in the front. a mess, but I got it back in eventually. So 3 sheet metal screws and then 3 machine screws into the standoffs, which were put in previously. And then there's this grounding strap that we made before that ends up going down here. Alright, and now the back panel is screwed on. Have to kind of rearrange the wires there a bit so none of them cast a shadow on the back of the meters for the backlighting, and I think I've got them so there's nothing in the way. And there's what it looks like so far from the front, complete except for putting all the knobs on the switches and sliders, and cosmetically the wood side panels, the sheet metal bottom, and the feet. And I think that's about it. The manual now goes to initial tests. I'm doing some preliminary tests according to the user's manual, and this entailed doing various continuity checks and checks for short circuits in the power supply and so on. And now I've got it plugged into my AC distribution panel, and I'm going to do a check of the power supply. Alright, I've got both LEDs on for some reason, I don't know why. Doing a check at this point in the power supply, I should be getting about 32 volts, and I am 31.42. So it looks like the power supply is functional. I adjusted the peak level pots on the rear panel to about their halfway point. They were pegged fully up, so that turned off the LEDs, so I guess I just had them set to maximum sensitivity. Alright, I've got the mixer set up on my recording bench, and I have a program that I recorded a number of years ago playing on my CD player, so I own the copyright to this, no copyright hits. It's paused, and I'm going to put it in play, and I'm going to advance the master controls. The gain on the left channel, or on this particular slider, is a little bit weaker than the other one. That may be just age of the pots or some other factor. Switch, that channel is off. I can put it to the right bus, back to off, put on the left bus. Right, off, left. biggest problem I'm noticing so far is that these switches, even though I've put deoxide on it, they're a little flaky. I'll seem to be getting very little feed through one channel or another, and then I fart around with the switches and then it comes in okay. So I don't think there's anything wrong with the circuitry. It's just aged electromechanical components that aren't completely working perfectly. But I didn't build this thing to use it. I just want to make sure it's working. So the sound is pretty clear. Pause it. Go to full gain. There's just the slightest tiny amount of hum and hiss. Very little. For the age of this equipment, that's pretty normal, I think. I've set the sensitivity up a bit. Okay, now I'm going to check all four of the mic inputs. I've got this dynamic mic that I use on my recording bench for doing narrations and voiceovers, and I just have it hooked up to a short cable. I'm plugging it into the first of the XLR jacks on the rear, and since that's on the mic 1 channel, I'm going to select that to the left bus, and I'm going to start talking. Testing 1 2 3 4, testing 1 2 3 4, testing 1 2 3 4, 1 2 3 4. As I recall from using one of these in the past, they were always a little bit hummy, even with the shielding and everything. So that's happening again here. At higher gain levels, you get a little bit of 60 Hertz in there. I was never completely satisfied with the level of hum on them. So let's see, that's the left bus, right bus, right bus, left bus. Turn that one off. Okay. Switch the second mic input to the left bus. 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 2 3 4. Switch the right bus. It's in the right bus. 1 2 3 4, 1 2 3 4, and bring it down. I've moved over to the third jack. Selecting the mic 3 input to the left bus. 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 2 3 4. Plenty of gain there. Again, some hum. Switch over to the right bus, and it's on the right bus. Equal levels. Turn it off, bring the fader down. Okay, I have the mic on the fourth input. The fourth one's a little different because it goes through a pan control rather than directly to one bus or the other. Right now it should be pretty much equal if I bring it up. 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 2 3 4. There's a little bit there, but it's not as loud as it would be if it was on one bus or the other. So I'm going to take the pan control to the left. 1 2 3 4, 1 2 3 4. Testing 1 2 3 4 on the left bus. You can see the light going there. Pan over to the right, and that one. Boom. Yep. Have to talk a little bit louder to get the light to go off on that one. Yep. There we go. Still got a little bit of that hum on there. Now some of that may be because I don't have the back on the chassis yet, and may be picking up a little bit from there, but I do remember the mic inputs being kind of hummy. Alright. So I decided to do another test to see if the line reversing switch on the back made any difference regarding the hum. So I've got my microphone plugged in again and it's plugged into microphone input 1, and I've got the main sliders up to around 7. I'm going to take the mic 1 input to about 5, and I've assigned it to the left bus. And let's see here. That's just talking into the microphone. Obviously it's being amplified a lot. Just doing it this way, it's not that apparent that there is hum. There's a tiny amount. Obviously I can get some feedback there. Testing 1 2 3 4. Testing 1 2 3 4. Switched over to the right. Testing 1 2 3 4. Testing 1 2 3 4. There's definitely hum there, but that's a pretty high gain level, more than you would normally need. If I have it down around here, you know, it's not that objectionable. I think most equipment, hi-fi equipment in the days that this product came out, had a little bit of hum in them. I certainly remember it. Nobody thought anything of it. But by today's standards, you expect to hear zero hum. You know, if it's there, it's so far down that it's inaudible. So we're more attuned to hearing hiss and hum and things like that that were taken for granted back in the old days. And you're hearing, you know, probably a reasonable performance for a fairly inexpensive consumer grade microphone mixer. But let's see if it does make any difference. I can hear just a little bit of hum. I'm going to move the switch. I don't hear much difference. Go back. There actually might be just a tiny amount of more hum in one switch position than the other, but it's pretty much negligible. Anyway, I wanted to do that experiment. Okay, I'm going to bring back the CD that was playing. Get the masters up about here and bring up the aux channels. Proof of operation. Everything's working. The only thing I haven't tested are the direct bus access jacks on the rear panel. I'm not going to. I don't have anything else to tie those into. Those are only intended to going to another mixer of the same kind to join buses, and I don't have anything handy like that, so I think this is a fully operational unit. The only qualms I have about it, like I said, there are some iffy spots in a couple of the pots. The switches aren't 100%. Sometimes you got to fiddle with them to get a good connection. And the aforementioned hum on the mic inputs that was not unexpected. But pretty clean sounding with just normal line level going through it. And even the amplified signal on the mic inputs is clean. It's just got that hum. So I think this is operating about as well as I could expect it to be operating. I have these spare brackets that are the 1/4 inch phone type jacks, in case I hadn't used the Canon or XLR connectors, and other hardware associated with those, lock washers, rings, nuts, and I also forgot to put in there the actual jacks themselves. And I've got them all ziplocked into a bag that tucks into this space right here, so they'll stay with the unit. In case, not that I'm ever going to do it, but what else to do with them anyway? They stay with the unit. And there's a final look before I box it up. And there's a final look before I button it up. And there's the bottom panel put on with 8 sheet metal screws and 4 bump-on feet stuck on. The adhesive still seemed to be pretty decent on them, so I did not have to replace or augment them. Last assembly step, putting on these wood ends. They're held in place by some longer sheet metal screws. Did I say final assembly? I forgot the knobs. They are the last step. Have to turn the page, Paul. There we go. Nice 1960s, 70s vintage look, but a pretty handsome piece of equipment. Got all the sexy sliders. And of course the nice slide switches, most of which are 3 positions, some of them are only 2 positions. Okay, there's the beauty shot. Alright, let's take a tour of the mixer. 4 microphone controls, 1, 2, 3, 4, each with its own fader or volume control, and each with a 3-position selector switch, assigning it to off, in which case that input does not do anything to contribute to the signal on the bus. You can select it to the left bus or the right bus, but you cannot select it to both buses. The same thing for mic 2 and mic 3. However, mic 4 is a little different. It does have an off position. Instead of left and right, it just has pan, and then it's assigned to the pan control. So if you've got it in the middle, it's sent roughly equally to both buses. If you go this way, it sends it entirely to one bus or entirely to the right bus. These days, most mixers would have a pan control on every input. And then we have two auxiliary inputs. Those are line level inputs, just like the normal, RCA type signal that you have on any piece of audio equipment. And that can be used for an output from a tape deck or a CD player or an MP3 player or whatever to bring it into the mix. And again, two sliders, and it can be assigned to left, off, or right for each of them. Then we have the master controls for the left and the right bus. What is the total volume coming off of that bus? And those buses run directly out to the rear panel, which we'll see, through an amplifier, which is what these controls do. The buses also run out unadulterated to the rear panel, but then they go through the final gain stage and then out to the panel as well. You have the meters, left and right, although it doesn't say left and right, and the two peak level LEDs. Normally you would have this in the plus 4 dB mode, but if the signal is too hot, you can put it here and then it has a different scale. The two buses can be left in stereo mode, where they're not affiliated with each other at all, or you can do mono, where the two buses are connected together so that the two signals are mixed between the two buses and both buses have the same mixed signal on them. And then of course the power switch. That's it for the front. So let's take a look at the rear panel. The four microphone inputs, 1, 2, 3, 4, have, in this particular build, XLR connectors on them, which were known as Canon connectors back when this kit came out. They can be either low or high impedance. If they're balanced, they must be low impedance. And there's a little recessed selector switch for each one. These are not phantom powered inputs. The microphones are probably intended to be dynamic microphones, which is what I've tested it with. If you wanted to run in condenser microphones, they either need to have their own batteries for power, or you need to run them through an intermediate phantom powering unit. So I don't know if this came out in the days prior to phantom powering, if it just wasn't common enough in consumer level products, but it doesn't have phantom powering. I actually contemplated modifying this to have phantom powering. It wouldn't have been that hard to do, but I wanted to leave it more or less unmolested. Of course, your line cord coming in, the line reverse, which can be used to reduce or eliminate hum under various conditions. When I tested this earlier, I forgot about that switch. When I was getting some hum on the mics, I should have tried the other switch position to see if it would make any difference. So, the actual auxiliary inputs are right here. They're just labeled 1 and 2, and that matches the nomenclature on the front panel. They're not yet assigned to buses, so it would be inappropriate to call them left and right. They get assigned by the switches here to left or right. So this would be, again, for a tape deck or any music source that's coming in stereo. Then you have the actual output, and this time it is left and right because that matches the nomenclature on the front. These are assigned buses left and right, and these are again line level signals just like these are, but these are inputs and these are outputs. And then the actual mixer bus, prior to the final output amplification, are available here, and these are inputs or outputs. They're just the bus. And the idea being that you can have more than one of these mixers set up side by side and connect these buses from one to the other, and thereby have a mixer with more inputs. You've got the peak level sensitivity controls, which are recessed screwdriver type adjustments. And those can be set any way you like to come on, to have the LEDs come on at the time you desire, whatever level that may be. And that's about it for the rear panel. Alright, there's the schematic for the TM-1626. We have over here 1, 2, 3, 4 microphone input channels, all identical. Well, nearly all identical. The mic 4 circuit has, as already been mentioned, an additional bit of circuitry that allows for the addition of a pan control. Instead of simple assignment of the channel to the left or right bus, 4 can be set up to pan between either one of them. Or it can be simply selected off, as all of these can be. And when you have the two line level inputs, these are from things like tape recorders, and it's buffering stage. There's no actual amplification here. And then some amplifiers for the left and right bus. These are the representations of the left and right bus, left and right, running vertically. Whatever's on the left bus gets amplified here, the right bus gets amplified here, and then there's a switch which allows you to select it for stereo or mono mode. In stereo, each circuit is treated independently, but in mono mode the two channels are just connected directly together, and therefore they influence each other equally, and the signals are essentially mixed to mono at that point. However, there are still output amplifiers, the left one and the right one, they're identical, and these have the master gain controls here and here. And of course, if you're in the mono mode, then both of them do the same thing. This is very similar to the amplifiers up here or here, except it adds a push-pull output stage, so they can drive things like long cables and so on, things that are outside of the immediate piece of circuitry. And then the left and right output jacks here and here. And then there's a comparator LED driver circuit, two of them, to operate the peak LEDs here and here. And the two rear panel controls for setting the peak levels that these two circuits respond to. And then the two different output channel right at the output jacks are fed up to this switch, which sends the signals through the diode bridges, which then directly drive the two VU meters. You can use the switch to pick whether these two resistors are put in series with the diode bridge or these two resistors are put in series with the diode bridge, thereby changing the sensitivity of the meters. And then finally down here we have the power supply section. It's a very simple power supply. There's only one voltage and it's a positive voltage. There's no bipolar here or anything like that. It's pretty simple. Now we'll get into the weeds. Alright, let's look at the power supply. I've left off for this discussion the transformer that's over here. I can pull up the actual schematic and look at that for a second. So we have the usual ungrounded plug here. There is no ground reference. It has a fuse protection for noise immunity from noise on the AC line. There's a shunt through a capacitor to ground. That's chassis ground. It's not earth ground. And then there's a selector switch, which determines whether we wire the two primaries in series or parallel for different voltages, 120 volts or 240 volts. And then we have, following that, the on-off switch. At the output we get something. I don't know what the voltage is. It's not specified. It's center tapped, but we're not using the center tap for the main supply. We take the overall secondary, run it through a diode bridge, and filter it. That's pretty conventional. And then we have our voltage regulator, which I'm going to discuss in a moment. But there is a AC voltage developed here, and there is a reference from that to ground, and that's put through the two incandescent bulbs in series going back to ground, and those illuminate the VU meters. Now here's my redrawn sketch of the power supply. So we come off the diode bridge, and we have, first off, a Zener voltage reference. This resistor and a Zener to ground. And that's a 36 volt Zener, so we get 36 volts here nominally. And that's applied through this resistor to the base of this transistor, which gets its collector voltage through this resistor from the same rough power supply up here. Filtered, but in no way regulated. And that causes it to conduct and apply a voltage to the base of this transistor, which is one that is designed to pass a bit more current. This is the series pass transistor. So if you just have this configuration by itself, you take this voltage and subtract the two base emitter voltage drops. That's 0.6 volts each, or 1.2 volts. And if you did nothing else, you would get about 34.8 volts here. And that's the output to the analog circuitry. And it's supposed to be 32 volts. So how does it get to be the 32 volts when it's trying to be 34.8 volts? Well, we have this feedback here. Oh, by the way, the output is also filtered. We have this transistor, and it has, from whatever this voltage is, another Zener voltage reference. This time it's a 27 volt Zener. So regardless of what the voltage is here, this point's going to be 27 volts. And that's applied to the emitter of this transistor. In order for this transistor to start conducting, the base must be roughly 0.6 volts. That's the base to emitter voltage drop, higher than this. So this has a threshold of about 27.6 volts. Now we have this voltage divider from the output, monitoring the actual output. And with the ratio here, if you had 32 volts here, you'd end up with 26.5 volts here. If the voltage is too high, then, for example, if you had 32.5 instead of 32, you'd end up with about 26.9 here. Still just a little bit less than this threshold, or the 27.6 volt threshold. If you had 33 volts up here, you'd be at 27.4, which is almost past the threshold. And if you had 33.5 volts up here, then it would be 27.8, which is definitely higher than this. So somewhere between 33 volts and 33.5 volts, let's call it 33.25 volts, the voltage here is now high enough to start turning this transistor on. And when this transistor turns on, it provides a path from here through the Zener diode to ground. Well, that steals current from this node here, the current that's coming through here. And because there's this resistor here, when you steal current from there, you have more current going through this therefore more of a voltage drop, and therefore this point here is no longer 36 volts. It's lower now because of this voltage drop. Therefore Q35 turns on a bit less. It turns Q36 on a bit less than it was before, increasing its resistance and thereby dropping more voltage until the higher voltage here, that 34.8 I mentioned, drops down, and it does that until it finds stasis, where it's conducting just enough here to steal just enough current from here to drop just enough here to reduce the voltages here and here until you get 32 volts. And I'd like to say that the opposite happens if the voltage goes too low, but it's not really set up that way. This circuit is always configured so it's trying to make substantially more voltage here, and this circuit can only throttle it down. It cannot do anything to increase the voltage, but that shouldn't be a problem. Now, there's this other little deal over here, this transistor that's wired emitter to collector across this Zener diode, and from the base there's a resistor and a capacitor to ground. At first I wondered what that did, and then I realized that when you first turn on this circuit, this capacitor is going to look like a short momentarily. So it's going to pull the base of this transistor down to here, which turns this transistor on since it's a PNP, which shorts out the Zener diode. Now there's enough current flowing to charge this guy up to the point where it doesn't turn this on anymore, but it's briefly turned on and briefly shorts this out, and then as the capacitor here charges up, then this progressively turns off, not abruptly, and then it gradually unshorts this guy. So if this is shorted, that means it's pulled down to ground, then there is no voltage here. There's no voltage here to turn this transistor on or this transistor on, and you get essentially nothing out here. So that's a soft start, basically. When you first turn the power on, this transistor makes sure that this develops no voltage, or at least very little voltage, and then, you know, in a very short period of time, probably less than a second, I didn't do the math, this is essentially no longer in the picture, and the voltage rises up to 32 volts and is regulated. And that's a thing that's in much better audio equipment. If you don't do that, then when you first turn on the circuit, you're going to get a big pop in the audio stream as everything kind of starts working, and you don't want that. So this circuit makes sure you have no power supply voltage initially, and then it comes up gradually so the circuit can start working, and by the time it's working and the volume level's high enough and the power supply is enough, then you shouldn't have that pop anymore. It's just there to avoid that. So here's a sketch I've come up with just to be able to describe the majority of the amplifier circuits in this kit. This is a classic circuit right out of the textbooks. I remember studying this one in college. It's usually just called the 2-transistor amplifier, sometimes called a 2-stage amplifier, but that doesn't mention the word transistor. You can see this same circuit with almost no variation in tons of audio equipment, especially from the 70s. So the goal here is to take a lower AC input voltage and amplify it to a higher AC output voltage. The kit produces a positive 32 volt power supply for everything. All the amplifiers are above ground, so ground's here plus 32 volts up here. There is no negative power supply, so everything is working above ground, at least within the amplifier stages. So this typical example, the 2-transistor amplifier has a input capacitor, and that allows an AC signal, something which is going above and below ground, to be coupled into this above ground only circuit. And then you've got an NPN transistor followed by a PNP transistor, and then another capacitor for coupling to whatever's downstream. And you can chain these one after another. You can come in, go through one, then do something, and then go into another one and do something, and then go into another one. Maybe you put a tone control between two of them, or a volume control between two of them, that type of thing. So let's look at basically what happens here. This little circuit here is pretty much a classic single transistor voltage amplifier. An NPN transistor with a collector resistor going to the positive power supply, and an emitter resistor going to ground, and then the base is biased with a voltage divider between the positive power supply and ground. So if you do nothing else, this resistor divider holds this at a particular voltage, and then that voltage determines how much current flows through the base emitter junction, and that controls how much the transistor conducts, and then depending on what these resistors are, that depends how much voltage you get out of it. And you can actually tap off of here or out of here. You know, out of here is probably the more common, but so this is something that everybody learns if they're studying transistor amplifiers. And of course you have to get a signal in, and that's where the input coupling capacitor comes in. Because there's a DC bias established by these two resistors. But when you couple in an AC signal above and below ground, it superimposes that voltage on the DC voltage here. So let's say this wiggles up and down by half a volt from zero, and these two resistors picked half of the power supply, for example. In that case, 16 volts. So you'd have a 16 volt voltage here when this is 0 volts, and when it goes up half a volt, you add half a volt and have 16.5 volts. When it goes down, you'd have 15 or 15.5 volts. So you're wiggling the DC bias up and down by the voltage of the AC signal. And then that influences the amount of conduction that the transistor has. And since this is sort of acting as another resistor in this resistor divider, then of course the voltages in the divider wiggle up and down as well. And that depends on several factors in the circuit, but suffice to say for the moment, like if we tap off of here, we're going to get essentially the same thing we got here, but at a higher voltage, and it'll be inverted. So when this is going up, this signal will be going down, and when this is going down, it'll be up. But again, this is all above ground, so the ground level is down here, not in the middle of the waveform. So this is just the same thing redrawn. We still have the two resistors for establishing the bias of the base here, and this is the collector resistor, and this is the emitter resistor. It's just shown over here because these two transistors are sharing that resistor. Now we go into another stage. Remember that this point here is the same as this but inverted and a higher voltage, and now that's applied to the base of this PNP, and the PNP works just like the NPN except everything's upside down. In this case, the output is taken from the collector again, just like it was here, but because it's a PNP, the collector is on the bottom, the way we've drawn it, and then that is passed out to the output circuit, and you've got a waveform sitting on there which has been inverted by this one, and some more gain added. And the way that works, just in a nutshell, is when you have a certain amount of current flowing through the base emitter junction of the transistor, there's a current gain that a transistor has called the HFE, and the collector to emitter current will be related to the base emitter current times the HFE. Therefore, you get some gain out of the transistor. And the same thing here. And then you add those two gains together. Now, there's not really any traditional feedback in a circuit like this. It doesn't really need it. If this were used in an instrumentation circuit, maybe you'd set it up so there's some feedback going back up to here. But this here is really working without any meaningful feedback. So it's not a precision circuit, but it doesn't need to be. The classic formula for gain of the entire circuit only involves these two resistors. It doesn't involve the HFEs of these to any substantial degree. Remember, these are just for biasing this transistor, and this is involved for biasing this. It's also the collector resistor, so I don't want to get into it in too great a detail. But the classic formula for gain on this, voltage gain that is these two resistor values added together and then divided by the value of the lower resistor. That gets you in the ballpark of what the gain is. In the first stage of the Heathkit, this is the microphone amplifier stage, but the circuits for the other stages are nearly identical except for the resistor values. Even the same transistors are used. We have 3.3 megs here, 220K here for biasing this, and then 120K here, and then 6,800 ohms over 680 ohms here. So that's a pretty simple formula. When you're trying to figure out how the voltage divider works, you add the whole resistance and then divide it by the bottom resistance, and that gets you the result, and that's controlling the emitter voltage here. And it all boils down to, with those component values, it should have a gain somewhere around 11. So whatever voltage is input, the output should be around 11 times as big. Now, I didn't use the same transistors, but I used the same circuit with the same component values and just built it up on a breadboard, and it had a gain that was in between 10 and 11. A little bit higher than 10, but not up to 11, so really close. And I ran it through a spectrum, just giving it a sine wave from a minuscule input, and then up to 0.1 volt peak to peak, and up to 1 volt peak to peak instead of 0.1 volt, and found that inputs up to 2.3 volts peak to peak were passed through with no problem. Once you got above that, you started clipping. One or the other of the transistors was no longer able to operate in its linear region, or it ran into the power supply without the ability to go any further. So a gain of approximately 10, maybe 11, and it was with the resistance values and with the capacitance values of a 0.1 microfarad and a 10 microfarad there, and other factors, it had a flat frequency response from 20 hertz up to 20 kilohertz, and considerably outside that range, but certainly in that sort of classic audio equipment frequency range. I didn't see any dip at all on the output as I ramped through the whole range of frequencies. Let's take a look at the circuit for the microphone inputs. You have a choice, depending on a switch selection, to either have a balanced low impedance input, typically from a microphone, or an unbalanced high impedance input. And this could be a number of things. It could be a very simple dynamic microphone. It could be the output of another piece of electronic equipment, but not a line level signal. You could probably plug in the input of electric guitar or something to this. You know, there's a number of things that are high impedance unbalanced. So let's look at the balanced one. The way balanced lines work, with audio and microphones in particular is, instead of just one wire to carry the signal and one wire for ground, there are two wires carrying the signal and one wire for ground. And the signals on these two wires are mirror images of each other. So when the signal goes above ground, the signal on the other one goes below ground, and when this signal goes below ground, this one goes above ground. Same exact voltages in phase with each other, just 180 degrees mirrored from each other. And that's imposed across the primary of a small transformer, which is an impedance matching transformer. It also unbalances the line. So it can be balanced on this side, meaning the mirror image signals, and then on the other side it's just a simple single-ended signal referenced to ground. Now of course these have to be referenced to something to have a signal on them, and there is still that ground connection. The reason for this is, well, there are several reasons, but the most simple reason is that when these signals are going to a higher voltage, plus here and minus here, between those two, the difference between them is a high voltage signal, or relatively high voltage signal. When the signals are near ground, then there's essentially no difference, so there's no voltage across here. When the signals start going to a higher and higher negative voltage here, higher and higher positive voltage here, once again there's a big difference between the negative excursion here and the positive excursion here, so there's a substantial voltage between them again, and now you've got a higher voltage across the transformer. So the transformer just sees one polarity of a signal going higher and then going lower and then going to zero and then going higher and higher in the opposite direction and then back to zero, just like the normal waveform. If there's some corruption on these, for example, if both of these wires are in a strong magnetic field and have some, AC signal induced into them, it's likely that they're both going to have exactly the same signal induced into them, and there's no difference between a component of these two signals if it's exactly the same. Normally it will never be exactly the same unless it's at ground. So noise signals tend to cancel out in this type of arrangement with the transformer. But then for amplification you want it to be single-ended again. So that transformer provides that. It also, because of the way it's wound, it allows this to be a high or a low impedance signal here and then a higher impedance signal here. The high impedance version just goes directly in without any modification whatsoever to the input of the amplifier, which is a relatively high impedance input, just as it was here. So low impedance translated to high impedance for a high impedance amplifier input. Already high impedance goes straight through with no transformer, and it's also not balanced, so it doesn't need the unbalancing functionality of the transformer. So a switch for each of the microphone circuits switches between this configuration and this configuration. Let's take a look at the basic mixer architecture. So once again, here are the left and right buses. They're just wires or traces on a circuit board. It's as simple as just a piece of wire or a conductor of any sort. Then we have our 4 microphone inputs, 1, 2, 3, 4, and I didn't show the input amplifier, which has already been described. That's the 2 transistor amplifier that boosts the input signal, and this is the output capacitor of that circuit, and by going from that capacitor through a resistor to ground, it ground references the signal. Going back to this, remember I said you had a ground reference signal here where the AC is going above and below ground, or 0 volts, and through this capacitor's functionality it couples that signal into the DC offset or bias that's here, so that the signal is now wiggling around on only the positive side of ground. So now we have the output of this, and we don't know what it's going into. It may be ground referenced, it may not, but it's typical to have a capacitive coupling between stages. So that capacitor here is the same as the capacitor here. Just visualize an amplifier circuit here, 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 and here. And then there's this resistor to ground, and that forces the output to be ground referenced again, even though it's going through the capacitor. So it's still single-ended, and we reestablished a ground reference. That means now when the signal here is wiggling around only on the positive side of ground, now because it's ground referenced on this side, now it's converted it back into an AC signal where it's going up and down, above and below ground, and more or less of it depending on where this potentiometer is set. If it's set up here, then you get the full voltage through. If it's set down here, this point is essentially grounded and nothing goes through. If you put it in the middle, then half of this gets put through, and so on. And now we couple those with a resistor into one or the other of the buses. There's actually a switch here, which I have not depicted because I'm trying to keep this simple. We always want both buses to have the same impedance, so regardless of how the switch is set up, it sees the same resistor value. And all these resistors here are the same value. If the switch on channel 1 is selected to the left channel, the resistor from the volume pot goes directly to the left bus. But we want to have the right bus see the same resistance. So we hang a resistor of the same value as this one from here to ground. Now it doesn't short it out because there's a resistor in between. All it does is essentially puts a 0-volt signal into the bus in place of a non-0-volt signal coming from here. This one is set up as if it's assigned to the right channel. So the output of the volume control goes directly to the right channel, and the left channel has a corresponding matched resistor value going to ground. So it always sees that the buses always see the same amount of resistance tied into them. Then here I've shown channel 3 as if it's turned to off. It's not assigned to either bus, in which case both buses have equal value resistors hanging off of them to ground. Now let's look at number 4. Instead of the switch saying put this channel to left or off or right, there is a switch that says we want to pan or not. And if it's not in the pan position, then the switch is open and the signal goes nowhere, which doesn't hurt it in any way. Assuming we are panning it, it goes through this buffer amplifier, which is just a simple transistor amplifier. It's just exactly like the first stage of the 2-transistor amplifier. It's like this much of it. These 2 resistors and this resistor and this resistor. A total of 4 resistors with capacitors on both sides. We just leave out this part. That's what's in here. And it's set up with resistor values such that it provides isolation and current amplification, but no voltage amplification. So the signal comes out of it just the same as it went in, although because it only has the 1 transistor, it gets inverted, so the signal's mirrored from what it was. Now in audio, that makes no difference. Whether you invert the signal or not going through all these stages, it does not change the way it sounds in any way. Then we have this duplicate circuit from the output of the buffer. 2 resistors going to the left bus, 2 resistors going to the right bus. And then in between those, the middle of these 2 resistor pairs is a potentiometer with this wiper going to ground. So if we have this in the middle, then this is a symmetrical circuit above and below. All the resistances are exactly the same, and the signal passes through equally to both the left and the right buses, so it's panned to the middle. Now if we turn the pot all the way over here, now the signal here gets grounded, shorted out to ground, and the left bus sees nothing, but it still has a resistor going to ground, and that's the same value as this resistor, which, by the way, is getting the full signal because it is not grounded. The pot's over here. Now if we move the pot to this end, then this side gets grounded, nothing gets through to the right bus, and the left side gets through to the left bus unmolested. Now let's look at the auxiliary inputs. Once again, we have amplifiers, but because we're not expecting any gain here, we're going from a line level signal to a line level output. There's just, again, a buffer amplifier similar to this one, a single transistor stage, and then you have the coupling capacitors, the volume controls, and the equal value resistors going to one bus or the other, depending on how you have the switch set up. In this case left, in this case right. The buses themselves are directly brought out to jacks so that you can use these as outputs. You can output the signals from the left and the right buses to other equipment, or you can actually put the output of other equipment into this as if they're additional points. Really, the way this is set up is if you have the need to have more than 4 microphones and 2 auxiliary inputs, you could have 2 of these mixers set up side by side and just plug the left to the left and the right to the right bus. So now you essentially have an 8-channel microphone mixer with 4 channels of auxiliary, and they don't know that they're 2 separate mixers. It just acts like one. These are not ideally set up to be used as outputs to other equipment, although you could do it. And then the 2 buses are brought out through amplifiers. These are actually amplifiers, not buffers. They boost the signal back up. They run through resistors, and there's this stereo mono switch. If the switch is open, then it's stereo, and both the left and the right signals go through unmolested. If you close the switch, then you're in mono mode, and it doesn't matter what signals are here and here. They're connected together, so coming out of that, they're both the same. They essentially get mixed together because of these 2 resistors. And the resulting signal here and here is now identical because it's mono, and the mono signal is the mixed value of the left and the right. And then finally we amplify it one more time and then send it out the output jacks to whatever equipment is out there. Alright, let's talk about the output amplifier. So after we leave the left and right buses of the mixer and go through an amplifier stage followed by the master volume control, we come to the output amplifier. It has the usual capacitive coupling, and the front part of it, this part of it here, is essentially just what we'd come to expect from a normal 2 transistor amplifier. We've got the first stage with the biasing resistors, the collector and emitter resistors. Here we've added a series capacitor to the emitter resistor. Then we go into the second stage, a PNP, and the emitter, as usual on this configuration, is tied directly to the V plus or positive power supply. The emitter, instead of having a simple resistor to ground, goes through these things in this path to ground. But otherwise it's just the normal 2 transistor amplifier. And instead of getting a little bit of feedback, which I alluded to before, I was reluctant to call it proper feedback in that previous discussion. But there is something coming from further downstream coming back to the emitter of the first transistor, and that's what this is. Just like here, there's a capacitive element to it. Now we take this output and we go into a push-pull stage. This is called an AB or a class AB amplifier. So it's a push-pull amplifier or a complementary amplifier, meaning that it can symmetrically pull the output voltage up or pull it down. And That's desirable for all sorts of reasons, which I won't go into here. When the signal here goes higher, then it turns this NPN transistor on more, which tends to pull this point up towards V+. When the signal here goes low, it tends to turn this PNP transistor on more, tending to pull this point down towards ground. In a basic theoretical sense, you could just have these two bases tied directly together and just have a resistor down here. So there's a path for the emitter current to go to ground. Problem is when you do it that way with the two bases tied directly together, because neither transistor can turn on unless there is a certain voltage between the base and the emitter. That's the base emitter voltage. And if you don't have more than that, then the transistor doesn't turn on at all. So you could get a situation where neither of these transistors are turning on and the output is not really connected to anything. So that's not ideal. It does cause a little glitch in the waveform of the output signal. So what you really want to do is set it up so both these transistors, when the signal here is near zero, is have them both turn on a little bit. So it's kind of pulling and pushing at the same time very gently. And that allows the transition from positive signals where this transistor is conducting entirely or exclusively to negative signals where this transistor is conducting exclusively. In that region where you're worried about whether you've got some distortion due to these transistors not turning on, these components here make it so they're both turned on just a tiny bit right near zero, and thereby avoiding the crossover distortion. And then we take the actual output signal and feed it back through these components to the emitter of the first stage of the two transistor amplifier, and that does provide voltage feedback so that if you start getting, if this stage starts running away or something where it's not behaving itself, that feeds back here and causes this to back off a little bit. So it's necessary with this type of stage to have some sort of a feedback, and that's how it's accomplished. And then once again we have a capacitive coupler on the output, because this is still only above ground, and we need to be able to get it back to ground referenced because the output is between this point and ground. So that capacitor allows that to happen. Now what if the output here is short-circuited? This could blow up these transistors. So there's a series resistor added here in addition to the capacitor. And then if you do have something connected out here which is causing a problem for these, instead of these guys having to dissipate all the extra energy, it's dissipated here instead and protects these. This resistor sets the output impedance. And on this Heathkit circuit, it's 150 ohms, so the output impedance is 150 ohms. Oh, I'd forgot to draw in this resistor. There's this load resistor here after the output capacitor and impedance setting current limiting resistor. There's this one to ground, and just like everywhere else, when you're going from a circuit that's only on one side of ground and you're trying to get it back to a ground reference or a 0-volt reference, you need to have a resistance going to ground to establish that, and that's what this guy does. Alright, here's the meter circuit. Quite simple. We take the signal from the output jack, it's the actual output signal of the mixer, and we apply it to the two-position selector switch, which is a meter sensitivity selector. It can be selected to either plus 4 dB full scale or plus 10 dB full scale. And either way, you get the output signal influences the current that goes through one or the other of these two resistors depending on the switch position. And then we have a diode bridge, and regardless of the polarity here, and remember this is at the output, so it is bipolar. It can go above and below zero, so the current can go either direction. And so the bridge here allows current to go this way. If it's positive, it goes this way through the meter. If it's negative, it goes the same direction through the meter. Hence the purpose of the diode bridge. There I added the plus and minus because the current's always going in this direction through the meter. Once again, if we have a positive signal here, it takes this direction. If we have a negative signal, then it's going this way and out. And it's really that simple. The resistance determines how much current flows through it, therefore a different voltage level here will result in more or less current adequate to make the meter move full scale. And let's talk about the peak detector. This is basically just going to flash an LED when the signal, the output signal, gets above a certain voltage that you've set. And you could think about that as a certain dB level, but it's just really, as far as this circuit's concerned, it's a voltage level. So this is the output of the AB amp. It's not the output of the mixer. This is tapped off right after the AB amp push-pull stage. So it's before the capacitor that returns it to a ground referenced level. So this is all above ground at this point. And it's also before the resistor that sets the output impedance. So it's before all that. We have a transistor here, and it's connected up with its emitter going to a voltage reference, which is adjustable by the peak level potentiometer. There's one of those for each channel, and this circuit is duplicated for each channel. When you've got a transistor set up like this, it's essentially a comparator. It's comparing this voltage against this voltage. And when this point is lower than this point by the emitter base voltage, the junction voltage, which is typically about 0.6 volts. So when this point is more than 0.6 volts lower than whatever this voltage is, then the transistor turns on and conducts. So what do we have here? We've got this pot, and with the resistor up here, it's limited to 13 volts, even though this is about 32 volts up here from the power supply. Because of this resistor, you can only adjust this peak level potentiometer between 0 volts and about 13 volts. And it's got a little electrolytic capacitor hanging on it just to stabilize the voltage here. And that's applied to the emitter. So anytime the signal here at the output of the AB amplifier drops lower than whatever this pot is set to in the 0 to 13 volt range, then this transistor will turn on. Well, what does that mean in the real picture here? Well, here's a illustration of the voltage ranges we're talking about. Power supply is about 32 volts, 0 volts is down here. Everything at this stage in the circuit is above 0 volts. We're going to guess that the biasing of the transistor amplifiers puts the virtual ground level at about half of the power supply. I haven't calculated that, I'm just assuming that that's about what it is. It would make sense to do it that way. So in other words, when the signal level, which is normally above and below 0 volts, when it gets to this stage, it's actually above and below 16 volts. So if you have a symmetrical waveform, it may go up to this point and as low as that point, all of it above ground and based around a 16 volt level. Assuming that's all true, and my previous experiments determined that the input amplifier could go as high as 2.3 volts on the input before it started distorting or clipping. With that amplifier having a gain of 10, we get an idea that the signal is probably going to be somewhere in the ballpark of 5 volts up to 27 volts. Now, that ignores the intervening amplifier, but I don't think that is set up to have nearly that much gain. It's really just to recover from losses on the bus circuit. So let's just assume that this is the range. It's going to go, the negative trough is around 5 volts, the positive trough is around 27 volts. And we're trying to detect when the peaks are getting too high. Well, since most of the signals are more or less symmetrical, if this is getting higher in this direction, this is getting lower or higher in that direction, or just lower. So let's say we had this pot here set to 13 volts. It's set up as high as it can go, so the peak is set as high as possible. We have 13 volts there. That means we can draw a line here that says 13 volts. When the signal gets more in this direction than the 13 volt level, then it's going to turn the transistor on. And that's the same as saying it's getting more than a certain level in this direction. Again, that's assuming that the waveforms are symmetrical, which they usually are more or less in audio. Now we could crank this down to 0 volts, which is here, and the waveform would have to go all the way down to here to get to 0 volts. So we're able to adjust somewhere in this area. And what if we set this to 5 volts up here? Then we would be setting the trigger level for the transistor right about at the point where we don't think the signal can get any greater in the negative direction or any lower in the absolute sense. So we can adjust, you know, somewhere in this area, which is the same as somewhere in this area, for when the transistor turns on. I hope that's reasonably clear. When the signal gets high enough to result in the transistor turning on, it starts conducting through here, and that applies an increasing amount of voltage to the emitter of this PNP transistor, which is also set up as a comparator, just like this one. In this case, the base is not coming from this, it's coming from this circuit up here. This is a resistor voltage divider that, because of the values here and the power supply voltage here, gives you about 5.6 volts. Then the LED comes off of that. This is the peak indicating LED, and it has roughly a 1.2 volt forward drop. So when it's on, it's going to drop about 1.2 volts, which means that nominally you'd have about 4.5 volts down here. That's 5.6 minus 1.2, approximately. Oops, I'd made some corrections and didn't correct everything. Be closer to 4.4 volts from this voltage dropping 1.2 volts. So again, this guy's acting like a comparator, and it always compares the base voltage to the emitter voltage, just like it compared the two here. So when this voltage increases to the point that it exceeds this voltage, then this transistor turns on. So remember that when this guy turns on, it can turn on more or less, but you're going to get a certain amount of voltage here. And when this point gets high enough to overcome the 0.6 volt emitter to base voltage here, so this has to get to be 0.6 volts higher than this voltage. 4.4 nominal plus 0.6 volts gives you 5 volts. So when this guy gets to be around 5 volts, then it turns this comparator transistor on, and it starts conducting in this direction, which turns on this NPN transistor, and when it turns on, it acts like a short and pulls this guy down to nearly ground. Well, that's fine, because now this is 0 volts instead of 4.4 volts. This is still higher than that, so this transistor stays on, which keeps turning this guy on, and they just stay on. And when this is on, now it provides a lower resistance path to ground, and now the LED can actually start having some current going through it, is enough to turn it on. And it stays that way until the signal here gets out of the range when this guy turns on, and therefore now this voltage drops, it becomes less than this, and it turns off again. So pretty simple circuit, really. 2 comparators and a driver for the LED.